Is Hodgkin-Huxley Action Potential relevant to MRI? Well, it should, but I don't know how to actually link it together. Yes, we can apply stimulation by pressing the Apply Stimulus button. Then you see an action potential. An action potential, shouldn't let you fire another action potential for a while, unless the channels they recover the potassium and whatever other channel. You have all the explanation at the bottom. So forget what the channel is, sodium and potassium. Which one is which? Sodium and potassium. And once they recover, you can fire again. Poof. You can set different parameters. So that's the kind of type of simulations we make. So don't forget to smash that like button. Yeah, magnet simulations. Well, that was kind of obvious. A thing to do, even though it's actually did a pretty decent job. So you can learn a lot about magnetic fields. For that reason, it will only let you maximum of 4 magnets are allowed. Big no. You ask for more than 4 magnets. So the simulation flips out. We can fix it later if that's a big problem, but obviously leave it as is for now. And yeah, we're doing what were we doing? MRI simulation. Well, I mean, it's related to action potentials because that's what you're recording in MRI, hopefully. Well, actually not. So it's actually not recording brain activity. Surprise, surprise. It's actually recording this quantum physics, whatever experiment. Of proton spin of electrons, protons, and then hopefully you're able to recover something useful. Obviously not getting an image out of it, it's just a sensor, a radio frequency, magnetic frequency like sensor, and then it gets reconstructed into an image. So here we actually show how the whole thing works, and I'm not an MRI expert. If there are any experts listening to this, do let us know. Let us know if this is correct at all or not. What's up with the... Okay, so you can actually use the slices. It's not very intuitive. I mean, if the image is just staying there, don't want like more controls to it or something, do we? Do we want more controls or not? Do we want more controls? Okay, we had the Claude making something. Did it finish the code? No, it didn't finish the code. That's why I don't see anything. Let's finish the code. Claude is normally not lazy.
All right, picture this. On the left, you've got these tiny little protons acting like they're at a chaotic proton party, and the B0 field is like this super strict bouncer trying to get them all in line. Then you hit the RF pulse, and it's like blasting music that makes them all start dancing in a crazy synchronized way. On the right, that black screen is like the empty canvas of an abstract dance performance. When the music stops, the protons start to chill out, and as they settle down, they emit these little signals that gradually form an image, kind of like the echoes of their dance moves. It's a strange ballet of physics, turning invisible movements into these intricate pictures. Pretty wild, huh?
Pretty wild, huh? Do we have... I don't know if a Claude made a similar simulation. Did it actually finish the code? No, it did not. Oh, Claude didn't finish the code. Claude didn't finish the code.
Hey everyone! So you're looking at the BioniChaos website right now. It's got these cool interactive tools for exploring things like quantum mechanics, neuron behavior, and even looking at retinal images. It's pretty neat for anyone interested in biomedical engineering or neuroscience. I'd totally recommend checking it out and letting the creators know what you think. Your feedback could really help them improve these tools. Now you're seeing a few more tools on the website. There's one for visualizing physiological signals, another for simulating brain stimulation, and even one where you can mess with neuron properties. Plus, there's a spectrogram generator and a brain EEG simulation. It seems like a really comprehensive set of tools for anyone interested in this kind of stuff. Seriously, give it a look and let the developers know what you think. They'd love to hear your feedback to make these tools even better. Awesome! Scrolling down, you can see even more tool stuff. There's a Fourier series visualization, and then something really interesting about AI understanding causality, which is a big deal in AI right now. And they've got a high-fidelity Fourier series simulation too. This website offers some amazing tools for visualizing complex concepts in biomedical engineering and neuroscience. Seriously, dive in and check them out. Your feedback is really valuable to the creators, helping them make these tools even better for everyone. Let them know which tools you find most helpful or interesting. Wow, look at all these tools. We've got this interactive report on the multimodal medical data landscape. That sounds super insightful for anyone looking at health data. And then there's an interactive guide to EEG technologies. Wondering how that breaks down those complex concepts. Plus, a visual analysis of cochlear limited. That could be really interesting for understanding the impact of medical technology. And look, there's a neurofeedback interactive evidence review too. These tools offer some incredible ways to explore medical data and technology. I'm curious, which of these interactive experiences seems the most engaging to you? And what kind of insights do you hope to get from them? Your thoughts would be super helpful for the developers, so definitely let them know what you think. Look at these! Now we're seeing even more interactive tools. There's an evidence review for neurofeedback. Curious about the latest research on that, huh? And then there's an AI-powered EEG speech decoding tool. Imagine the possibilities for communication. Plus, a modality comparison chart, which could be super helpful for understanding different measurement methods. And don't forget the cochlear simulator and advanced EEG simulator. Amazing for learning and experimenting. Seriously, these tools offer so many unique ways to engage with complex information. What aspects of these simulations are you most excited to explore? And how do you think they could help you understand these topics better? Your feedback is super valuable to the developers, so don't hesitate to share your thoughts. Wow, the BioniChaos website has so many fascinating tools. We've got an interactive evidence review for epilepsy and cardiac health, really digging into that complex relationship. And then there's a synthetic noise generator dashboard, perfect for experimenting with different signal types. Plus, an interactive explorer for public multimodal biomedical datasets. That's a goldmine for researchers. And an ECG simulator and FNARS interactive viewer add even more incredible capabilities. It's amazing how many different areas these tools cover. Have you found any particular tools that sparked your curiosity the most? And what kind of possibilities do you see for using these interactive features in your learning or research? Your feedback is incredibly valuable to the creators, so please do share your thoughts and help them make these tools even more impactful. These tools are just incredible. Now we're seeing an interactive cochlear implant simulator. How amazing to explore that technology. And then there's Rhythm Scan for analyzing EEG data and detecting seizures with machine learning. That's a powerful combination. Plus, a joint time-frequency scattering tool for seizure detection adds another advanced approach. And the Seer Medical Interactive Case Study provides a real-world perspective. Finally, the EEG device comparison is super helpful for evaluating different devices. These tools really demonstrate the incredible diversity in biomedical technology and analysis. What kind of insights do you hope to gain from exploring these particular tools? And which ones seem the most relevant to your interests? Your feedback is invaluable to the developers, so please take the time to share your thoughts and help shape the future of these interactive resources. And the list of tools keeps getting more impressive. We have the Stentrode, a minimally invasive brain-computer interface. That's groundbreaking technology. And the Biomedical Data Types Explorer is a fantastic resource for navigating different kinds of biological data. Plus, the Forecast Trap provides a critical analysis of seizure prediction technologies, which is so important. And the Hearing Aid Simulator offers a practical understanding of sound amplification. Finally, PaperViz is a fantastic tool for visualizing research papers. It's remarkable how these interactive features make complex topics so much more accessible and engaging. Which of these tools do you think would be most beneficial for your learning experience? And what kind of unique insights do you hope to gain from interacting with them? Your feedback is incredibly valuable to the developers, so please share your thoughts and help them continue to improve these amazing resources. There are some incredible tools on the BioniChaos website. We have the myoscope for visualizing EMG signals, great for exploring muscle activity, and then there's SpectraWave, a real-time audio spectrogram visualizer, fascinating for sound analysis. Plus, the Biomedical fields visualization uses a Venn diagram to show the intersection of different areas, really helpful for understanding the bigger picture. And MyoMock lets you explore EMG signals through a simulator. Finally, the ChatGPT Author explores the role of AI in scientific writing. It's amazing how these tools cover such a wide range of topics. Which of these interactive features do you find most intriguing? And what kinds of questions do you have about their specific functionalities? Your feedback is really valuable to the developers, so please don't hesitate to share your thoughts and help them make these resources even more helpful. This interactive MRI simulator is a fantastic addition to the BioniChaos website. It perfectly complements the other interactive tools by providing a hands-on way to understand the complex principles of MRI technology. Being able to adjust parameters like the B0 field strength and RF pulse intensity and see the resulting changes in the proton spin simulation and MRI image is an incredibly effective way to learn. It's like having a mini MRI scanner at your fingertips. This interactive approach really helps demystify a complex medical imaging technique. What kind of features did you find most helpful in understanding the process? And are there any other aspects you'd like to see integrated into the simulator? Your feedback is crucial for the developers to make this tool even more effective and user-friendly. Don't hesitate to share your suggestions. Based on the context of the interactive MRI simulator, I would expect the Play Demo button to initiate a demonstration that walks you through the key steps of an MRI scan. It would likely show how the different parameters, like the magnetic field strength and the RF pulse intensity, affect the proton spin simulation and ultimately contribute to the generated MRI image. It would basically provide a guided demonstration of the simulator's capabilities, making it easier to understand the relationship between the settings and the resulting image. The application is split into two main parts, the simulation on the left and the resulting image on the right. The goal is to see how your actions in the simulation panel directly affect the generated MRI image. Proton spin simulation, left. This canvas shows a group of proton spins, the small arrows. In their natural state, they are randomly aligned. Use the B0 field strength slider to apply a strong external magnetic field. Notice how the protons align with the field and begin to precess or wobble around the field's axis. A stronger field, higher Tesla, T, results in a faster precession. The RF pulse intensity slider sets the flip angle of the radio frequency pulse. A 90-degree pulse will tip the spins fully into the transverse plane. Click Apply RF Pulse to excite the protons. You will see them tip over and spin in unison, in phase. This synchronized spinning generates the detectable MR signal. After the pulse, the spins will gradually dephase, spread out, and return to their original alignment. This is known as T2 and T1 relaxation. Resulting MRI image, right. This canvas displays a slice of a synthetic brain. The brightness of each pixel depends on the MR signal intensity from the corresponding region in the simulation.
Okay, so I actually had the Gemini talking to ChatGPT and actually fixed the problem together. So one can actually view what's on the screen. We described the problem briefly and actually summarized it for the developer. The demo mode wasn't working correctly. So when changing stuff, it wasn't actually applying the RF pulse before. Now it does. So it will change something, apply the RF pulse, so you can actually see the image. Okay, so now it's actually working correctly. If you can quickly summarize, but also, do you think we can run the demo continuously for it not to stop? How would you go about it? Okay, so this is working really well now. Can you just very briefly review in a conversational text what the changes were made?
The changes involved ensuring the apply RF pulse function works during the demo by removing the if is demo running return condition. This allowed the demo to trigger RF pulses and dynamically update the MRI image as intended, aligning the functionality with the expected behavior.
Okay, this is great. So it's working now perfectly well. Thank you very much. Now, how would you go about running the demo mode continuously for it not to stop unless the user is interacting with the page or pressing the play demo button again or something?
To make the demo mode run continuously until the user interacts with the page or presses the play demo button again, you can modify the run demo function to loop indefinitely.
So when we're playing the demo, first of all, we want it to be continuous, but second, we want the parameters to adjust to be different parameters. So it's essentially be continuously showing how the application is working, but potentially maybe not just looping through the same cycle, but just modify or making the cycle longer. What do you think?
Instead of looping through the same fixed sequence, you could introduce randomness or gradual changes to parameters like the B field strength, RF pulse intensity, or brain slice. This way.
Okay, so how would you practically go about it, modifying the code?
To make the demo continuous and more dynamic, I would modify the run demo function to include a loop that keeps running until the user stops it. Instead of repeating the same sequence, I'd introduce variations in the parameters, like randomizing or gradually changing the B field strength, RF pulse intensity, and brain slice.
Okay, that sounds good. Can you actually modify the code? Just go ahead and modify the code to make the demo mode continuous as discussed, and just comment along in conversational style what changes are made to the code.
The code is now updated so the demo mode runs continuously, picking new random values for the MRI parameters each cycle. You can stop the demo at any time by clicking the Stop Demo button, which toggles back to Play Demo when stopped. Here's how the new demo works. Now, when you hit the Play Demo button, the simulator goes into a continuous demo mode. Instead of just repeating the same steps, it randomly changes the three main parameters, B field strength, RF pulse intensity, and the brain slice each cycle. So, you'll see the magnetic field strength slider move to a new value, the RF pulse intensity change, and the brain slice jump to a different section, all automatically. After each adjustment, the demo applies an RF pulse so you can see the effect on the proton spins and the MRI image. This keeps going, with new random values each time. However, there are a few things to consider critically. First, how smooth is the transition between parameter changes? For example, when the B field strength slider moves, does it feel natural, or does it jump too quickly? The animate slider function should ensure smooth transitions, but if the duration is too short, it might feel abrupt. Similarly, the pauses between actions, like waiting for the RF pulse to relax, need to be balanced. Too short, and the demo feels rushed. Too long, and it might lose the user's attention. Another question is about the randomness of the parameters. While randomization adds variety, does it always produce meaningful or educational results? For instance, if the RF pulse intensity is set to a very low value, the resulting MRI image might not change much, which could confuse users. It might be worth constraining the randomness to ensure that each cycle demonstrates a clear effect, like always including a 90 degrees pulse at some point. Then there's the issue of user control. The demo stops when the user clicks the button again, but what happens if they interact with the sliders or other controls while the demo is running? Does the demo override their input, or does it pause to let them explore manually? It might be helpful to disable manual controls during the demo or provide a clear way to switch between demo and manual modes.
I think it's working great. I don't know. Yeah, we did ask it to critique the thing, which it did, but yeah, we could add the annotations. Moving on, onto talking about the annotations. So during demo mode, what kind of annotations would you display and where would you display them not to obstruct the simulation?
During demo mode, annotations should be minimal yet informative, providing context without obstructing the simulation. For example, parameter changes asterisk display a small floating label near each slider, e.g., B field, 2.5T, when it changes. These labels could fade out after a few seconds to avoid clutter. Current action asterisk add a subtle overlay at the top or bottom of the screen with text like applying RF pulse or switching brain slice to explain what's happening in real time. Educational notes asterisk use a small, semi-transparent box in a corner, e.g., bottom left, to display brief educational tips, such as higher B field increases precession frequency. Interactive highlights asterisk highlight the active slider or control briefly, e.g., a glowing border, to draw attention to the parameter being adjusted. These annotations should be non-intrusive, fading in and out smoothly, and positioned away from the main canvas areas to keep the simulation visually clear.
Okay, can we start introducing the annotations during demo mode? There is some space below the two canvases, essentially below the simulation and above.
You could add a dedicated annotation bar or box that updates with brief, clear messages about what the demo is doing, e.g., increasing B field strength to 2.5T, applying RF pulse, 90 degree, switching to brain slice 5, etc.
Okay, a question about the field strength. So currently it's going from 0.5 Tesla all the way up to 3 Tesla. Can you explain this range?
The range of 0.5 Tesla to 3 Tesla represents the typical magnetic field strengths used in clinical MRI machines.
Okay, so just continuing from that point, so why stop at 3 Tesla? Why not go higher? Can you respond based on whatever current research?
Going beyond 3 Tesla is certainly possible and is already being explored in research in specialized clinical settings. Higher field strengths, such as 7 Tesla or even 10.5 Tesla, offer significantly improved signal-to-noise ratios and spatial resolution, which can be beneficial for detailed imaging of small structures like the hippocampus or for studying microvascular changes. However, there are practical and safety considerations that limit their widespread use. First, higher field strengths increase the risk of specific absorption rate, SAR, heating, which can pose safety concerns for patients. Additionally, the cost and complexity of building and maintaining ultra-high field MRI systems are much higher. Artifacts, such as susceptibility distortions, also become more pronounced at higher fields, which can complicate image interpretation. Finally, regulatory approvals and the need for specialized training further limit their adoption in routine clinical practice. So, while higher fields are exciting for research, 3 Tesla strikes a balance between performance, safety, and accessibility for most clinical applications.
Okay, but we live in a simulation, so how would you change the slider to include the higher Tesla options? And if we do, how would it affect the actual visualization on the simulation?
If you want to include higher Tesla options in the slider, you could extend the range of the B field strength slider to, say, 7 Tesla or even higher. This would allow users to explore ultra-high field MRI scenarios.
Can you summarize the visualization impact in a conversational style? Make it fun.
So, imagine cranking up the Tesla slider to 7 or beyond. Things get wild. First, the protons in the simulation would start spinning like they're on a caffeine high, thanks to the Larmor frequency skyrocketing. The canvas would be buzzing with faster, tighter precession animations, making it visually dynamic but potentially chaotic if not handled smoothly. The MRI image on the right would glow brighter, as higher field strengths mean stronger signals. But here's the twist: at ultra-high fields, artifacts might sneak in, like little visual gremlins, distorting the image. It's a trade-off, more detail but also more quirks to deal with. And the sound? Oh, it'd be like turning up the pitch on a Theremin, higher and sharper, maybe even out of human hearing range. You'd need to scale it down to keep it fun and not ear-piercing. It's like giving the simulation a turbo boost but making sure it doesn't spin out of control.
Did you just mention the Theremin? Can you explain what that is? Make it...
The Theremin. It's like the magical unicorn of musical instruments, because you play it without even touching it. Invented in 1920 by Leon Theremin, it's an electronic instrument with 2 antennas. One controls pitch, and the other controls volume. You wave your hands near these antennas, and voila, it produces eerie, otherworldly sounds,
like a sci-fi movie soundtrack or a ghost humming in the attic. It's basically the OG of electronic music, and playing it feels like conducting an invisible orchestra. If you've ever heard the spooky whir in old horror films, that's probably a theremin showing off its haunting charm.
How's it relevant to MRI imaging? Just keep it brief.
The theremin is like the MRI's quirky cousin in the world of physics. Both rely on electromagnetic principles. MRI uses magnetic fields and radio waves to image your insides, while the theremin uses electromagnetic fields to create spooky, touchless music. In a way, the theremin's eerie sound could be the soundtrack to the mesmerizing proton spins in your MRI simulation.
Yeah, everything we do is eventually available on BioniChaos.com. You can go check it out. So essentially play with all the tools and web applications that we make straight away, all by yourself. Actually, I had another version of the webcam filter. Didn't make it to production. Yeah, if you have any comments, if you actually went, even if you just went and checked the website, do let us know. We do want to hear your opinion and what's your experience like.